So activity 2, first one, points in 3D space, vectors for direction and movement, matrices for geometric data manipulation under chapter 2. Points in 3D space. Points in 3D space are mathematical entities that represent specific locations within a three-dimensional coordinate system. Each point is defined by a set of three coordinates x, y, and z. The x coordinate represents the position along the horizontal axis. The y coordinate represents the position along the vertical axis. And the last one, the z coordinate, represents the position along the depth axis, extending into or out of the screen. So together, these coordinates specify the exact location of a point relative to a chosen reference frame. Points in 3D space serve as the fundamental building blocks for representing objects, shape, and scenes in computer graphics and engineering, architecture, physics, and other fields. They enable precise positioning, transformation, and visualization of three-dimensional data, making them essential in a wide range of applications. So, characteristics of points in 3D space. Position. Each point is defined by its unique position within the three-dimensional coordinate system, specified by its x, y, and z coordinates. Second, coordinates. Points have three coordinates, which is x, y, and z, which determine their location relative to a chosen reference frame. Dimensionality. Points in 3D space exist within a three-dimensional environment, allowing for movement and positioning along three mutually perpendicular axes. Distance. The distance between 2 points in 3D space can be calculated using distance formulas such as Euclidean distance, which measures the straight line distance between 2 points. Location relative to origin. Points may be located relative to the origin or any other reference point within the coordinate system. 6. Visualization. Points in 3D space can be visualized using graphical representations such as dots or markers to denote their positions within a three-dimensional environment. Last one, which is transformation. Points can undergo transformations such as translation, rotation, scaling, and shearing, which modify their positions and orientations within the coordinate system. And understanding these characteristics is essential for accurately representing and manipulating points in 3D space, enabling various applications in fields such as computer graphics, engineering, physics, and more. So, example of point in 3D space in this picture. In this picture is an example of vector in 3D space. So, vectors for direction and movement. In 3D graphics, vectors are crucial for representing directions and movement. They are typically used to define positions, orientation, velocities, and transformation of objects in three-dimensional space. Here is an example of vector in 3D space. So, characteristics of vectors for direction and movement. So first, which is magnitude, represents the size of length of the vector, indicating the distance or scale of the movement. 2. Direction specifies the orientation or heading of the movement, often described using angles or directional terms. 3. Which is addition and subtraction. Vectors can be added together or subtracted to represent combined or relative movements. Scalar multiplication. Vectors can be multiplied by scalars to scale the magnitude of the movement without changing its direction. The last one, which is vector operation. 5, which is components. Vectors can be broken down into components along different axes, which is e.g. x, y, z in 3 dimensions, allowing for analysis for analysis of motion in multiple directions. Unit vectors, which is special vectors with the magnitude of 1, often denoted by z, and k in 3 dimensions, used to specify direction without affecting magnitude. Last one, which is vector operation, include dot product, and cross product, which have application in calculating angles between vectors and determining perpendicularity. So these characteristics make vectors powerful tools for representing and analyzing directional quantities in various fields, including physics, engineering, and computer graphics. So, matrices for geometric data manipulation. Matrices are widely used for geometric data manipulation due to their ability to represent transformations such as translation, rotation, scaling, and shearing in a concise and efficient manner. So here are some key ways matrices are used in geometric data manipulation. The usage of matrices in geometric data manipulation. Transformation representation, which is matrices can represent geometric transformation in various coordinate systems such as 2D or 3D. For example, a 3 by 3 matrix can represent 2D transformations like translation, rotation, and scaling, while a 4 by 4 matrix can represent 3D transformation including translation, rotation, scaling, and perspective projection. 2. Composite transformation, which is multiple transformation can be combined by multiplying their corresponding matrices together, enabling complex transformations to be applied sequentially. Homogeneous coordinates, which is matrices are used in homogeneous coordinates to represent points, vectors, and transformation in a unified way. Projection, which is matrices are used to represent perspective and orthographic projections, essential for rendering 3D scenes onto a 2D screen. Coordinate system, matrices are used to convert between different coordinate systems such as Cartesian, polar, or spherical coordinates, facilitating transformations between different geometric representations. Last one, which is graphic pipeline. Matrices play a crucial role in the graphics pipeline of rendering engines, where they are used to transform vertices from object space to world space, then to camera space, and finally to screen space for display. So overall, matrices provide a powerful framework for manipulating geometric data, enabling the representation and transformation of objects in various dimension and coordinate systems. So, thank you.